Everyone. As we get started and we get ready to go into these videos, I just wanted to explain a little bit about making these videos and what you'll expect to see. In each week, I expect to have a couple of videos. I'll try to keep the slides somewhere around 10 to 15. And so some weeks you'll have more videos, some you'll have less. But we've chosen topics that are commonly missed on tests or quizzes, or just a little bit confusing for students coming in, whether it's from my classes in undergraduate A&P, or it's for students in the MABS program who we've known over time have struggled in these different areas. And so we are trying to make these videos to help ensure that you have another source of information walking you through some of the more difficult physiological concepts. So that's the purpose for these videos. I hope you find them helpful. And I wanted to also make them a little bit shorter so that you could watch the video, read the section of the textbook, maybe even watch it again. That will give you the time to really digest the material and begin to understand it before you move on to something else. Because each of these slide decks, when you look at the whole thing, there's a lot of slides and it's a lot of material and it moves quickly from one topic to the next. So we want an opportunity for you to kind of break it down into some smaller chunks and begin to understand those chunks a little bit better before you move on to the next one. So this one will be our first video for the neurophysiology chapter. This one is really starting you out at just an understanding of intracellular and interstitial fluid movements, ion movements, and what will allow a cell to hold a resting membrane potential, because the next video, when we talk about an action potential or how a neuron is going to send a signal, we can't have an action potential unless we know what makes up the resting membrane potential. So this video is going to be the foundation for what we're going to talk about in the next two videos. First, we're going to start with just a basic description of the different categories of fluids. You have a couple of different slides that talk about this in your slide deck. You actually don't have this one, and I will on occasion throw some slides in that aren't part of the slide deck of the textbook that you have, and that's okay, because it's just additional pictures or additional information that I think is helpful, and I think you'll find when you watch these videos that it will supplement the material that you have in your slide deck. This is one of those that isn't in your slide deck, but it's just helpful, especially for students coming in, to be reminded of the different types of fluid categories that the body has. So we have plasma. Plasma is the fluid base of blood, and plasma is primarily contained within the capillaries. So the capillary wall with the endothelial cells will hold the plasma inside, but you'll notice these blue arrows. So that means that we do have ions and we do have fluid moving in and out and exchanging the plasma contents with the interstitial fluid contents. Most of those fluids are easily able to move between plasma and interstitial fluid. Now, some things can't move through, like red blood cells, white blood cells. Those are kind of stuck within those capillary walls. In the interstitial fluid, notice that that is fluid between capillaries and cells. That is what interstitial fluid, and it makes up a pretty significant portion of the body's fluid as a whole. We're going to see that on the next slide. This one down here is transcellular fluid. Transcellular fluid is the fluid, of course, within the cells. So its boundary would be the cell wall or the epithelial and connective tissue making up that cell. We see some of that again, intracellular here, transcellular between, intracellular within, and the cell membrane or the plasma membrane is going to encase that. So this is the fluid inside of the cell. This bullet point right here just talks about the movement of nutrients, the movement of ions in and through and across some of these cellular walls, and we're going to talk about that in a couple of slides as well. This is another picture. in kind of a chart format that gives you the relative proportion or breakdown of the ion components within the different types of fluids. So over here in part A of this figure, we have the blood plasma making up a small percent of the total body weight and not as much of the fluid as you would imagine. Here we see interstitial fluid. Again, that's the fluid between cells and tissues, making up about 15%. And then the fluid that is within the cell making up the majority overall. You'll notice here that the plasma concentrations of your electrolytes like sodium and chloride are very similar to the composition of the electrolytes in the interstitial fluid. And that's just because, again, as evidenced by their drawing of the capillary here, it's fairly leaky in that these ions can move back and forth between these fluid components here and between these compartments, between plasma and interstitial fluid. So you see, I hope you can see right here, that sodium makes up a high percentage of plasma and interstitial fluid, whereas potassium makes up a low percentage. Then as we look over here into the intracellular fluid compartment, we see a very different composition. We see that potassium makes up the majority of our intracellular fluid, and sodium makes up a very small percentage. And that can be separated by the cell membrane here, and that's the reason why the sodium and potassium are so different across those two compartments. Also, while we're here on this slide, I want to remind you that while you're looking through your slide decks, please be sure to check the notes section of PowerPoint. In the notes section of PowerPoint, you will likely find some notes in each of the PowerPoint slides. Maybe not all of them. There are some slides that maybe don't have notes. But a good number of slides will have notes in the notes section that will help with explanation and perhaps things to highlight in that particular slide. For example, another thing to highlight on this slide as we're talking about our electrolytes is just reminding you of what a cation is and an anion is. So a cation is a positively charged ion. So those would be things like sodium and potassium. And even calcium. Then the anions are the negatively charged. So generally, those are things like bicarbonate, protein, and chloride ions. So it's really important to remember, and we're going to talk about this in just a minute, how our interstitial fluid has more sodium and our intracellular fluid has more potassium. In order to talk about the movement and resting membrane potential, we have to understand our types of membrane transport. This is probably a review for almost everybody, so I will move fairly quickly through this section on the slide, but reminding you of two types of processes. Passive transport means that the substance, typically we're talking about an ion here, but the substance is moving from its area of high concentration to low concentration, and no energy is required to do that movement. All particles, including ions, always want to move from their area of high concentration to low concentration. So that's what we see in this figure here. These red particles are highly concentrated on this side of this plasma membrane, and they have a low concentration over here. And so as long as this channel is open, these ions are moving down their concentration gradient, or in other words, from the area of high concentration of the ion to the area of low concentration of the ion. When you talk about active transport, that's where the particle is moving against the concentration gradient. It is moving from the area of low concentration to high concentration. It is not natural for an ion or a particle to move against the concentration gradient. And in fact, because it is not natural, it has to use some energy. Some ATP is required, and oftentimes then what we call this channel is called a pump, because it's pushing or it's driving the movement of a particle against its concentration gradient. Down here we just have a reminder of some categories of transport, that diffusion is a type of passive transport. This right here is a figure that illustrates diffusion, and in fact it's called facilitated diffusion in this case because there's a carrier that's facilitating or helping that diffusion. You have carrier mediated, so if you have a type of carrier or a protein within the cell membrane, and so that can be active or passive. And then vesicular transport means that oftentimes you pinch off a piece of the cell membrane to move something, and that requires energy. In this slide, we're talking about why we need to have different channels on the cell membrane. And ions, because they're charged, they have a positive charge or a negative charge, so those are cations or anions. Because they're charged molecules, they can't cross the phospholipid bilayer, the plasma membrane, without a channel. The channel is really important to get those ions across from one side to the other, whether they're going into the cell or they're going out of the cell. So this slide summarizes some of the different types of channels that we have. First of all, what is a passive channel? A passive channel means that it can be open all the time, and the ion can move across the cell, whether it's going from inside or outside. It's going to move from its area of high concentration to low concentration. So these will allow ions to diffuse across the plasma membrane. They will diffuse from their area of high to low. So we call them leak channels. Leak channels just meaning that because they're always open, the ions can leak across the plasma membrane. The active channels or gated channels are only going to open when you have energy or ATP in order to open them. And because they're active or gated channels, then these are going to allow the ions to move across in the opposite way of their concentration gradient. And sometimes it may allow them to open and move through the concentration gradient, so from high to low again, but it has to be opened chemically or voltage gated. So this gate is literally like a gate that blocks something from coming through unless you have a signal. A chemically gated signal means the binding of a chemical. Usually it's a neurotransmitter. So if the neurotransmitter binds, the channel opens or the gate opens. Another type of channel that is gated is a voltage gated channel. That just means that if the ion concentration across the plasma membrane reaches a certain level or a certain millivolt, as this one is showing right here, then the channel will open and close. And in the next couple two videos, we will actually talk about neurotransmitters, opening channels, and we're going to talk about voltage gated channels. Since these are gated channels, they're not open all the time, so nothing can leak through. They're only open when they are triggered. And the trigger, again, it can be a chemical or it can be voltage gated. And when the trigger ends and the trigger's taken away, the signal, then the gate closes again. So there's a lot of control over gated channels. Finally, the last thing on this slide is talking about how membrane channels are specific to the ion that's passing through them, so that you have sodium-specific channels and potassium-specific channels, and even calcium-specific channels. Certain ions moving through certain channels. Now that we know that ions cannot just cross the plasma membrane by themselves, and we know that there are different types of channels, leak channels and gated channels. Sometimes we have passive diffusion, sometimes we have active diffusion. Now we can begin to understand why we can get a membrane potential. What is a potential? A potential means that you have a difference in the charge of the ions across the membrane. So if you look at this figure, we have a cell membrane here. This side marks the inside of the cell. Notice it says intracellular here. This side marks the outside of the cell, or the interstitial space, which is also the extracellular fluid. So the same thing. This cell membrane is separating these two compartments, this compartment from that compartment, and these ions cannot cross this plasma membrane. They cannot do it. They can only cross if there is a channel to allow them to do so. So we have the creation of a membrane potential because we are now separating charged particles, usually oppositely charged particles, across the membrane. And that creates and stores, if you will, a kind of potential energy. And this potential energy is measured as voltage because the voltage is a difference between the charge. How much positive charge you have versus how much negative charge you have. Now, interestingly, if you look at this figure, I hope you see this little plus on the left-hand side and the minus on the right-hand side. What we have when we talk about a membrane potential, or in just a minute, we're going to talk about how we generate this resting membrane potential, is that all cells have a negative resting membrane potential. They are negative relative to the outside of the cell. So the inside is negative relative to the outside. The majority of the reason that that is true is because these large proteins, so the large A here is negatively charged proteins, so they're big anions, which is why they put an A there. So they're big negatively charged proteins, and they're stuck inside of this cell. They cannot get out. So they hold that negative charge. And in addition, we're going to talk in just a minute about the movement of potassium, and that's what we see right here. Mainly potassium. Potassium is really going to drive the reason why we have a negative resting membrane potential. The last thing I want to say on this slide before we talk about how we generate the resting membrane potential is that it can range from -50 to -100 millivolts. We're going to talk about the neuron specifically in a little bit, but just understand that all of the cells of the body have a negative resting membrane potential, and they may vary a little bit, but we will focus in on the neurons soon. Over this slide and the next slide, we will talk about kind of 6 steps that cause us to generate a resting membrane potential and why it is negative. So kind of the first thing, it's not necessarily number 1 because this is continuously happening, but if we had to kind of set up the scene for you, what begins in our cell, here we have the inside and here is the outside. We start with one of our potassium and sodium pumps. So a sodium-potassium pump. These are pumps. So what does it say? When we see the word pump, it's going to tell us that we're looking at something that is moving ions across their concentration gradient, and it requires ATP. So that word pump is a very big clue to you that you're talking about something that is moving ions against their concentration gradient. So we're moving sodiums and potassiums against their concentration gradient. So let's remember what we talked about before. So when we discussed the movement of sodiums and potassiums, we have 3 sodiums for every 2 potassiums in this pump, which is interesting. So before we even get to number 2, this pump doesn't move sodium-potassium equally. It's not 3 sodiums and 3 potassiums. Interestingly, it's 3 sodiums for every 2 potassiums. And notice it is ejecting sodium from the cell, so it's pushing them out, and it's pulling or pumping potassium back in. So we're moving sodium out and potassium back in. And that's against the concentration gradient because we already had a lot of sodium on the outside and we had a lot of potassium on the inside. So notice that. That was our resting state before. We already had sodium on the outside. If you go back a couple slides, you'll see that. Sodium was high on the outside, potassium was high on the inside. So that's why we have to use a pump, because we're continuously doing that even more. We keep pumping more sodium out and more potassium in. 3 sodiums out for every 2 potassiums in. Now, not only do we have this sodium-potassium pump, But number 2 says we also have these potassium leak channels. The potassium leak channels are opening without, any ATP or anything like that, and they're actually letting potassium leak. So a leak means we're moving from an area of high potassium to low potassium. So that's potassium right here is going to leak its way on outside of the cell because it's really high inside and potassium doesn't really want to be there. So it will just leak its way on outside of the cell. So because we keep pumping out 3 positives, so stay with me here, 3 sodiums, 3 positive sodiums for only 2 potassiums, and the potassiums keep leaking their way out, notice what's happening. We're getting more positives outside than we have inside. More positives are going outside than inside. So let's see if we can do that. So every time one of the pumps turns, we have 3 sodiums that we pump outside the cell, but we only pump 2 potassiums to the inside of the cell. So notice, even with one turn of the pump, if you will, we're automatically getting a net positive over here. So 2 turns, now we have 2 net positives. 3 turns, we have 3 net positives. It's not going to take very long before you have a lot more positives on this side than you have on this side. And add to that a reminder of the potassium leak channels. As we keep letting these potassiums leak through that channel and go to the outside of the cell, more and more, we're going to get the inside of the cell being generally negative. Sorry, that circle didn't work very well. And the outside being generally positive. And one last reminder while we're here before we look at some of the others is the large anions. We don't really see them in this particular picture, but we definitely have large proteins stuck inside. On the last slide, we said that with our sodium-potassium pump, we were moving 3 sodiums out and 2 potassiums in, and our leak channels, because of the potassium, was causing it to leak out, right? So our chemical gradient of potassium, our chemical gradient, means potassium wants to go where potassium is less. It doesn't like to hang out with other potassiums. So wherever there's less potassium, it moves from its area of high concentration to low concentration. So if we're talking about the chemical gradient of potassium, potassium wants to move out of its leak channel. But what's interesting, do you remember that we just at the last slide talked about how the inside of this cell is negative, right? So let me draw that in again. The inside of this cell, let me circle it actually, is negative compared to the outside of the cell. Well, what is potassium? Potassium is a positively charged ion. And remember that positive charges are attracted to the negative inside. So what's interesting is we have a chemical gradient, so I'm going to put a C, that makes our potassium want to go this direction. So that's interesting, right? Potassium wants to go out because there's more potassium here than there is over here. But we also have, I should have given myself more room here, an electrical gradient where potassium actually wants to go this way. Why does it want to go this way inside the cell? Because potassium is positively charged, and here's our negatively charged inside. So now we have this push and pull, if you will. We have a chemical gradient that wants to make potassium go this way. We have an electrical gradient that wants to make potassium go that way. So this first point, number 4, we have the electrical chemical gradient pulling the potassium back inside the cell. So now we have potassium is moving through the leak channel from one side to the other until it reaches generally a steady state. And that's what we call the resting membrane potential. The resting membrane potential is the steady state where there's about equal movement of potassium from one side to the other. Now, please understand this does not mean that nothing moves. It's not a stop, but it just means potassium electrical gradient has about equalized its chemical gradient. Most of the cells, this is somewhere around -70 to -90. Sorry, see that negative right there? It's -70 to -90 millivolts. That's a typical resting membrane potential. Then our definition for resting membrane potential is the electrical voltage across the cell when the cell is in a resting or inactive state. So it's not sending a signal or doing a change. And again, it's driven by the concentration of ions, predominantly potassium, that is determining that resting membrane potential. And here is the value we want to remember moving forward, that the resting membrane potential for neurons is -70 millivolts. So that's how much the inside is more negative by a measure of -70 than the outside of the cell. So the last slide we have here is just a picture representation of the axon of a neuron. And notice again, it's just reminding you the inside of this axon is negative relative to the outside. -70 is this resting state. So this is what we have to remember moving forward as we get prepared to talk about an action potential.